Hello and welcome back. So, last time we were talking about polynomials, and we finished with this principle here. It says that a polynomial of degree d is uniquely determined by its values at d plus 1 points. So, what exactly does this mean? So, to make this a little more precise, let f of x and g of x be polynomials of degree d, and suppose you have d plus 1 distinct points. Okay, by points of course we mean real numbers or complex numbers or whatever it is that you are plugging into the polynomial. So, let us say real numbers for our purposes. Let these be distinct real numbers if so if f of xi equals g of xi for these d plus 1 distinct points x1 x2 till xd plus 1, then the polynomials f and g must actually be the same, they must be equal to each other. Okay. So, that is what this principle means when you sort of write it out in a little more detail. So, let us see how would you actually prove a statement like this. So, what one does in many such things where you must prove that two objects are equal is you sort of consider that difference. Okay. So, let us prove this statement. So, here is a proof. Let us define or let us consider a new polynomial called h of x, which is just the difference between f and g. Now, what all do we know about h? Well, here are the various things we know. Fact 1 is the degree of the polynomial h. So, observe f and g are both degree d polynomials, and when you subtract or add two degree d polynomials, what you might get is, well, possibly something of degree d, but could also be something of strictly smaller degree than d. Okay. So, let us just be content with the following: the degree of h is at most d, is less than or equal to d. That is statement 1. Statement 2, is that h vanishes at these d plus 1 points x1 x2 till xd plus 1. Okay. Now, observe that the second statement means that these d plus 1 points are roots of this polynomial h. Okay. So, this sort of already violates the thing we looked at last time, which is that a polynomial of degree d can have at most d distinct roots. Okay. So, here is a polynomial whose degree is at most d. So, it could not possibly have more than d roots. Okay. So, observe therefore, so how do we now show? Let us just complete the proof formally. If h is not 0, if it is not the 0 polynomial, then, so let me just say if h of x is not 0, by which I mean it is not identically the 0 polynomial, then it has degree okay. So, I should just be a little careful here. So, either, since I kind of made a distinction last time, so either h of x is 0 or it is non-zero and has degree at most d. Okay. So, if h of x is not 0, then it is a polynomial of degree at most d with more than d roots, in fact with at least d roots, because here are d plus 1 roots, it could potentially have even more than that. So, it is a polynomial of degree at most d with greater than d roots, and that contradicts something that we already saw. Okay. So, that is really the proof that a polynomial of degree d is determined once you know its values at d plus 1 points. So, this sort of suggests the natural next question, which is given prescribed values at d plus 1 points, can you find explicitly a polynomial which takes certain prescribed values at those points? Okay, so what I mean is something like this. So here's the interpolation question, here's the problem statement. Let x1 through xd plus 1. So what is d? Let d be a positive or non-negative integer. Let x1 through xd plus 1 be distinct real numbers So those are the points at which I will prescribe some values. So and what are those values? Let y1, y2, yd plus 1 be any real numbers. I don't need them to be distinct. So the problem is the following: find a polynomial, let's call it p of x of degree at most d, which has the property that it takes the value yi at the point xi. Okay. So in somewhat more graphical terms, what this says is something like the following: you take some distinct real numbers. So here I have taken d equals 3, so I have 4 numbers x1, x2, x3, x4, and at each of these points I prescribe some y values. So I give you y1, so maybe that's y1. At x2 I give you some value y value y2, let's say this is y3, and x4 I give you some y value y4. So I have 4 points. This point is x1 comma y1, this is x2 y2, and similarly okay, x3 y3, x4 y4. So I have 4 points a, b, c, d, and what this question really is asking here is to explicitly find a formula for a polynomial of degree at most 3, okay, a cubic polynomial, at most a cubic. So I could potentially have a smaller degree polynomial whose graph passes through these 4 points. I am looking for a polynomial whose graph will pass through these 4 points. And further I am looking for a polynomial of degree at most 3, that is the other important thing. Okay, so that is the interpolation question. This is what is called a polynomial like this is said to interpolate between these 4 points. And so observe that we already know something from this principle right here, which is that if at all such a polynomial exists, we do not yet know that it does, but if it does exist, then it is certainly unique. There can't be 2 different polynomials which satisfy this property. Okay, and why is that? Because of what we just said. If I have, suppose I could find a polynomial p and maybe another polynomial q, both of which had degree 3 and had the same values at these 4 points, then according to that principle p equals q. Okay. So note, so here is the first thing already, that so let us make some observations on this. Note, if such p exists, it is unique. Such p of x exists, it must be unique. Okay. Why? By this principle that we just talked about. Okay, that is one. Now let us do, to get a sense of this, we will just do some special cases. So let us do some special examples. So let us take the case when d equals 1, okay, in the interpolation problem. What does that mean? It means that you need to find what are you given. Firstly, you are given 2 points x1, x2, and you are given 2 y values. So I am given y1, y2, so I have x1, y1, and I have x2, y2. And the question says, can you find a polynomial whose of degree at most 1, whose graph passes through these 2 points. Okay, so what do I want? I want a polynomial p of x of degree at most 1, okay, passing through these 2 points such that p of x1 equals y1, P of x2 equals y2. Now observe that a polynomial of degree at most 1, well, let us say a polynomial of degree 1 is just a straight line. The graph of such a polynomial is a straight line, okay, because what does a polynomial of degree 1 look like? So P has degree 1 means P of x looks like, let us say, oh, okay, fine. So it looks like this, a1x plus a0, right. There is a constant term and a coefficient of x. So the graph of such a polynomial is of course just a straight line. So this question really boils down to the following: given 2 points, find the equation of the straight line joining them. Okay, so that's the interpolation question at d equal to 1, and of course that's a that's a well known solution. We know how to do this just using our usual notions from coordinate geometry. So let's just recall the solution to this problem. So what's the equation of that line? Well, here's one way of writing the equation of the line. You say y equals, so I'm going to use what's called the slope form of the equation of the line. So I know the slope is y2 minus y1 by x2 minus x1. So that's the slope, and so let's write it in slope form. It says y minus y1 by x minus x1 is the same as y2 minus y1 divided by x2 minus x1. So this is the equation of the straight line which passes through those 2 points. So let's just simplify this a little bit. Okay, so I'm going to write it as follows. I'm going to write it as y equals something. So I'm going to simplify this. So I'm going to get y2 minus y1 times x minus x1 plus what do I get, plus of y1. Okay, so I'm going to rewrite this once more in the following form. I will write it as something times y1 plus something times y2. So I want to do the following. I want to write it as y1 times some expression which does not have y1 or y2 plus y2 times some expression. So I am going to try and rewrite it in this form. So let us do that. This looks like y2 times x minus x1 by x2 minus x1, x minus x1 by x2 minus x1, and I have a y1 which occurs here as well as a y1 there. So if you sort of see what the y1 coefficient looks like, okay. So here's another way of rewriting the same expression. So I've just done a little bit of manipulation. You should check that this is correct. So it is y1 times x minus x2 divided by x1 minus x2. Okay. So that's the equation of the line. So here's the polynomial. Here's the polynomial p of x that we want. Okay. So let's y is just another name for the polynomial p of x. So here's the solution to the interpolation problem at for the case d equals 1. Okay, so we're just going to do something. So we'll soon see that in fact this has a very natural generalization. So I'm going to call these 2 polynomials as something. So let's call this polynomial in the first box, which multiplies y1 as p1 of x, and the thing which multiplies y2 as p2 of x. So observe that p1 and p2 have the following property, that this polynomial p1, p2 have, well, let's write down their properties. They are both of degree exactly 1, have degree 1, and they have the following interesting property. If you take p1 and you evaluate it at x1 and x2, so this is p1. If you put x1 for x, then what you get here is just 1, whereas if you put x2 you get a 0. Okay, so this is what p1 is, and if you try the same thing with p2, it is the opposite, it is 1 on x2 and 0 on x1. Okay. So you have these two polynomials which have these two nice properties that they are 1 and 0 on x1 and x2. Okay, so that sort of suggests a general way of attacking this problem. So let us just do interpolation in the general setup. So let us just do it for any d. Okay, so let us just try the general interpolation problem. Let us take any d positive, and so what are we given? We are given those d distinct points. Okay, so what we will try and do is the following. Let us try and find a polynomial which has the following property. It is 1 on exactly one of these points and 0 on all the other points. Okay, so here is a problem. You take any one of these as let j be any one of let it be any one of these numbers, fix any one of them, and let us find a polynomial called Pj such that it has the following property of degree d such that Pj is 1 on xj and 0 on all the other x's. For all I between 1 and d plus 1 except for j. Okay. So we will see in a moment why this is useful, right, but it is sort of a generalization of what we have done right there. We found a polynomial which should be 1 on exactly one of these points and 0 on all the other points. Okay, so first let us try and solve this problem. How do we find a polynomial which vanishes on all the xi's other than on this single point xj? Okay. So here's the solution. Remember we have already done this last time. If you know a root of a polynomial, you know that xi is a root of this polynomial, then we know that this polynomial can be written as x minus xi times something. Okay. So observe that p of x, or we are calling it pj of x, since it vanishes on all the xi's, it must, each of them must be a factor. So it should look like, for example, if j is 3, then pj of x should look like x minus x1 should be a factor, x minus x2 should be a factor, and so on. In general, all the x minus xi's, so let us write it as product so pj of x must certainly have all of these as factors, product of all the x minus xi's except for I equal to j. Okay. And notice that this is already of degree d, right. So this is already a degree d polynomial because it has exactly d factors, and what I wanted is a polynomial exactly of degree d. So I can't really have any more factors here. What I could have is some constant in front. Okay. So let us say pj of x might look like some constant times the product of x minus xi. Okay. So already we are able to get quite a lot of information just by knowing that here are d roots of this polynomial. And now to find this constant, we use this last piece of information. It says that if you plug in x equals xj, then you should get a 1 on the left hand side. So now observe, putting this condition in, this gives us the value of c. Okay. What is the value? If you put x equals xj, the left hand side is a 1, the right hand side is a product of xj minus xi. So the constant c must in fact be 1 over the product xj minus xi. So this is a product over all I from 1 to d plus 1, but I is of course not equal to j. Right, that is the choice of the constant which will make this a 1. Okay. So well, what have we done? We have at least managed to solve this problem. If you want to find a polynomial of degree d which is 1 on a single point and 0 elsewhere, well, here is the answer. It is just product x minus xi, I goes from 1 to d plus 1, divided by product xj minus xi, product I goes from 1 to d plus 1. Okay, and observe it is a lot like what already worked here, right. So in a sense this is the instance of that principle for d equals 1. So now why is this useful? So what do we have? So we now have many polynomials. We have polynomials p1, p2, pd plus 1, right. We have a formula there which works for every value of j, which have the following properties such that, what do we know about them? Well, they are all of degree d, degree of pi equals d for all I. Well, by all I mean all I from 1 to d plus 1, and property 2, which is sort of the key property, is that pi vanishes on xj. So pi evaluated on xj will give you 0 if I is not equal to j, and it will give you 1 if I equal to j. Okay, so it has this really nice property about this, and using these polynomials pi you can solve the general problem. So recall what is the general interpolation problem. It says find a polynomial which takes the value yi at xi. Okay, so here is the solution to the general interpolation problem. So general interpolation, what I have given, you are also given these real numbers yi. So we are also given the values, not necessarily distinct real numbers. Okay. So what we do is define a polynomial p of x. So let us define polynomial p of x to be, well, we know all p1 through pd plus 1, you just say it is y1 times p1 of x plus y2 times p2 of x till y d plus 1 times p d plus 1 of x. Okay. So you combine these solutions here by multiplying them with the yi's, okay, is what is often called a linear combination of the pi's. And now observe that this polynomial has all the properties that we want. So what are the properties of p? Firstly, observe the degree of the polynomial p. So each of the pi's is of degree d, and what you are doing is you are sort of taking a linear combination, you are multiplying them by various constants and adding the answer. That could very well end up being a polynomial of degrees smaller than d as well. Okay, it is less than or equal to d for sure. So that is property 1, and property 2, which is the key thing that we want, the value at xi. So if you observe what is the value when you put x equals xi, well, all these terms other than the ith term will actually be a 0 when you put x equals xi. Okay, that is the key property here. Only pi of xi will contribute a 1, all the other terms will give you a 0. So in fact only the ith term comes up, so this is basically lots of zeros. The ith term contributes, it gives you yi times the value of the polynomial is 1 plus a bunch of zeros again. So that is exactly the yi that we want it to be. Okay, so this is precisely the solution to the interpolation problem. Okay, so just do an example here. Suppose I want d to be 2, and I give you 3 points x1, x2, x3 to be -1, 0 and 1, and we take some values of y, just some arbitrary values 1, 0 and 5. Like I said, they need not be distinct, here they just turn out to be. So here let us just do this whole thing. So observe that the y's do not really enter the picture until the very end, so I do not need to worry about them right now. If I know the x's, I can compute my 3 polynomials p1, p2 and p3. So let us calculate those 3 polynomials. So p1 of x, according to this prescription, is it's x minus 0 into x minus 1 divided by this -1 minus 0 into -1 minus 1. So that's my formula for P1. So this is nothing but if you sort of work this out, it's half x into x minus 1. Similarly P2 of x, so you sort of do the same thing again. So let me just write down the answer. It is 1 minus x square. P3 of x, similarly it turns out to be half x into x plus 1. Okay, in order to do this, all I have done is just plug into my formula right there, and the final step, the interpolating polynomial, which is the linear combination of these three, would just be obtained by multiplying the first answer by a 1, the second answer by a 0, and the third answer by a 5. So the interpolating polynomial p of x, remember, is nothing but y1 p1 plus y2 p2 y3 p3 of x. So in this case, if you sort of just work this out, turns out to be 3x squared plus 2x. Okay, so I am just leaving the details, something you should certainly work out by yourself. Now observe that this in fact does do the job. If you plug in x equal to 0, it gives you a 0. If you plug in x equals minus 1, it's 3 minus 2, which is a 1, and if you plug in x equals 1, it's 3 plus 2, which is a 5. So this guy in fact does do the job. And if you sort of look at the graph of this fellow, it's in fact some sort of parabola like this. The value at so at minus 1 the value is something is 1, 0 the value is 0, and at 1 the value is something. So it's a parabola which sort of passes through these 3 points, this point here, the origin, and this point there. Okay, but here's the general principle, and so this procedure here that we talked about goes by a name. It's called Lagrange interpolation. Okay, something that will work in complete generality no matter what your value of d is.